In our introduction to engineering probability and statistics, we're going to do a lot in this course by developing ideas and what you might call theory in the context of letting it emerge from examples. In our first example, we're going to take a look at quarter-inch polypropylene braided rope, the typical kind of product that you might see at a hardware store, home improvement store, or one of your discount kinds of stores, and the type of product that people often use out of their garage to tie something down in the bed of their pickup truck, or maybe hang up a bird feeder, that sort of thing. So some of the typical kinds of engineering questions you might be asking in the context of this particular product might be directly associated with the manufacturing process, where you might be asking the question, as you've pulled samples off of the line, you might be asking, is the product, or is it meeting specs? Specs might have been from a whole variety of different kinds of specifications and of different kind of nature. There's also the question of what is the rope strength. Now, we ask these questions really in different contexts, potentially, because you could be specifying that the rope, this particular product, meet a certain strength specification, so that'd be more of a manufacturing kind of perspective. But if you were starting to think about it from an engineering design perspective, you might be thinking about the strength in a totally different manner. And if you're thinking about it from a marketing standpoint of what are we going to actually list on the package, what the rope strength would be, it's both a marketing and a product liability kind of perspective. You might be asking this kind of question. So a natural thing that you might do is pull some samples off, and for simplification, let's represent this braided rope as though it were a single braid, maybe made of many fibers. And one of the tests that we might then do is a simple pull test. And we'll talk in this course about how you might design what the random sampling procedure would be, and how many should be in that sample at what point in the process, and how do you interpret the results. We'll actually focus more on interpreting the results than setting up the design of the experiment. But all those little parts will be in this course. And so we might have pulled off 3, as is commonly the case, and have results would be 412 pounds, 522 pounds, and 469 pounds, the results of our sampling process. So sampling is size 3 in this particular case. And what do we make then of that? These numbers are not all the same, that they have some variation. Is some real significant questions result in, or come along of, hey, is there something going along in our manufacturing process that has led to this different variability? Is one of these just a defect? You might be tempted to say, well, defect might be something that's too low, but if we're trying to produce a rope of a certain kind of strength, certain size, and we have one that's too large, that could represent wasted material, something that's inefficient. And if it's outside of range, then you could have a defect high just as much as having a defect low. So there's a lot of interesting different kinds of questions that you might be going along with here. Another kind of perspective here, though, is that we might go back to our basic mechanical model for this uniaxially loaded component and think about this from just mechanics in a slightly different kind of way, where we might say, well, the strength of our rope that we've observed over here, theoretically, that might be thought of as equaling to a material strength, a stress, times some cross-sectional area, and then because our theory that we're getting here is not going to match, plus then some air term. So this first part is what we get out of a basic mechanics of materials type of class. And then here's another term that we throw in so that our theory will then match somehow more accurately what we end up with in the observed world. Ooh, wait a minute. Match up with the observed world. What's really going on here? Well, the part that I want to emphasize right at this moment is that we can understand a little bit of this difference between what's happening here in the theory and what we have observed over here by recognizing that this stress, being a mechanical property of a material, is coming inherently from material variability. And that as well, when we produce this 1/4 inch polypropylene braided rope, the area of that rope is also going to have some variability. That's the geometric variability or dimensional variability. And then also, even if we include variability in the material and the geometric part, there's going to be other influential factors that we have not included. And the variability then that goes along with those. Some of that is going to be things such as, have we included creep during this test? And since this polypropylene braided rope is very much subject to creep, then we can anticipate that part of the difference in our theoretical results and our observed results might very well be something like creep, and we might want to adjust our model as a result and include some other sort of creep term. Rate of loading, for instance, would be important. Temperature would be important. Right? Other factors that may contribute to this scatter of the results are such things as stress concentrations and how we've clamped or somehow grabbed onto the ends of our sample and pulled. And we have some standards for how to conduct these tests that talk about how you begin to do that and to eliminate some of those sort of influential factors. And that's good for the testing standpoint, but what about when you put it out into practice? Those are other factors that come along. And then there's factors that we can't anticipate or we don't really understand. And so now this error term also includes all those other aspects as well. Right? And again, one of the key things to consider is that in this course we'll be looking at how do we deal with this data here and interpret it, analyze it, pull it out. And you already know some of the things inherently, that you'll know some of these things about calculating averages, but what do we do with that average, and how do we know whether this data set is representative, and what does that average even represent? And when in cases where we have mechanical models that are sort of natural that we might use to understand these results over here, then well, that's all well fine and good, but again, there might be some additional aspects here in that model that are maybe not perfect. And that leads us to sort of a generalization of the key aspects of this course that really become the reason why we have this kind of course, and that is all about really variability. Variability and, in a broad sense, uncertainty. In the following kinds of way. And one of them, which we've already mentioned, and that's inherent variability, such as we're going to get out if we produce this material in this polypropylene, we're going to get some natural variation in the material properties. Now, things such as steel are a little bit easier to control than things that are more of an organic type of property sometimes. And so the amount of variability, and that'll be something we begin to characterize, is going to change, of course, from context to context, and whether that variability is significant or important to us or not is going to be something we'll discuss. There's also modeling uncertainty. Already sort of introduced that in this kind of context, that we don't know that this mechanical model we have up here for the rope is really a perfect example or a perfect model, whether in fact, actually, we can be fairly confident it's not a perfect model, because there's going to be scatter that's not explained by just P equals sigma times A. And so that's part of the uncertainty that might come along. And then this notion that we add the error term in here to account for all these other influential factors is another part of that modeling uncertainty. So there's two areas where we see both variability and uncertainty that we'll be characterizing in this course. And then we'll do statistical quality control. And that goes along the lines of how do we conduct sampling while we're producing a product so that we can understand what's happening in the manufacturing process and whether or not something about the process is going in or out of control. And then we'll introduce two additional aspects, and that's risk and industry standards. Right, now the notion of risk, or something that's riskier than something else, here in the engineering world needs to be handled in a very careful kind of way. The major aspect of the notion of risk is really a consequence of something bad happening. Right, so if we go back to our polypropylene rope example, if this is a fishing line, or it's this polypropylene rope, or it's a structural steel cable, the instance of this fracturing, right, it gets pulled to fracture, has vastly different implications in consequence to human activity. Although it doesn't have to be restricted to human activity, that tends to be the way we think about it for most cases. Now, if you're into environmental consequences, then of course it's not just a human activity, it's more broad and holistic, right? So, but there's clearly a significant difference in the consequence of a fishing line breaking as compared to a polypropylene rope breaking and then getting into a structural cable. And that notion of consequence to human activity is typically measured on the scale of how does it influence society as a whole, and particularly in terms of life safety. Now, in more recent years, we started to think about risk also in terms of an economic risk. And when you start thinking about, well, what's the consequence of a hurricane, not only to life safety issues, but the economic impact, and then the potential also consequence to human suffering and misery during the recovery events, begins to be a larger, more holistic view of risk. And we've started in the engineering world and to begin to develop tools that will help the public policy decision process in many of those kinds of instances. Right? So risk, though, is very much associated and in connection with hazards, but it is predominantly focused on the consequence of human activity. And the kinds of concepts and tools that we're developing in this course are set the stage for then developing models to make decisions about risk. And then industry standards are a variety of ways to begin to try to provide a systematic way of approaching this question of, say, material variability or even geometric variability. Right? And the industry standards, of course, now are going to vary on every single industry and sometimes within branches of that industry. So, for instance, in my world, the structural design world, how we approach the industry standard associated with the production of concrete versus the production of steel have a lot to do with those different industries, and also a significant amount to do with the inherent variability and our ability in a quality control standpoint to be able to do certain things with those different materials. And concrete, for instance, is a much more difficult material to control in terms of the variability we end up with in, say, the 28-day compressive strength of the concrete as compared to steel, where we can much more tightly control the variability that we end up with. And of course, there's some also associated consequences of how much money does it take to create the infrastructure that will allow us to have that kind of control. Right? So industry standards play a significant role here in our understanding of variability and uncertainty, and these tools that we're going to develop in this course will be the foundation to a lot of what you'll see in later courses as you get directly into things such as decision analysis and quality control, or if you go off into other design worlds and developing models associated with design standards.